All right, hello, welcome to a chapter 3 video this time. We're going to look at section 3.1, which is on measures of center. So these are, you've heard me actually refer to them, but these are things that we consider to be sort of what the layperson, the non-statistician would call sort of average, typical, expected values, right? So things that represent something that's typical or average. The focus of this section is to obtain a value that measures the center of a data set. In particular, we present measures of center, including the mean and the median. Our objective here is to not only find values of each measure of center, but also to interpret those values. So mean and median are the two main things that we use to measure center, typical average values. In fact, the mean is what you've been calling average your whole life. So in the third grade, when you learned to average a bunch of test scores and you added them all together and divided by the number that you had, right? And you called that the average. Well, that's what we call the mean in statistics. And actually it's calculated exactly the same way. The only difference is we use slightly different notation, right? And median, most of you probably know, you've seen this in math at some point in your life. It's the middle value. Another measure of center that we're going to look at here is the mode. The mode is the value that occurs the most often. All right, so measure of center is a value at the center or middle of a data set. The mean or arithmetic mean of a set of data is the measure found by adding all of the data values and dividing by the total number of data values. That's what I just talked about. So what you called average in the third grade is what we call the mean in statistics. Sample means drawn from the same population tend to vary less than other measures of center. The mean of a data set uses every data value. And a disadvantage of the mean is that just one extreme value, an outlier, can change the value of the mean substantially, right? Using the following definition, we say that the mean is not resistant, right? The mean is not resistant. Means it's very, very affected by an unusual value. Yeah. A statistic is resistant if the presence of extreme values does not change it very much, does not cause it to change, right? So the median would be something that's more resistant than the mean. We'll talk about why, but it's resistant if the presence of extreme values, outliers, doesn't change its value very much at all. All right, and so new notation, this is what I'm kind of talking about. So yes, we're going to calculate it exactly the same way, but we have a lot of new notation. So that first funny looking E there, that's called sigma. It's the Greek letter sigma. It's actually capital sigma, and it denotes the sum of the data values. X is an individual data value. So if we have 10 data values in our sample, each one of those is an X. So we have like the first X, the second X. We usually call those X sub 1, X sub 2. So each data value is an X. So in algebra, X is usually something unknown. In statistics, it refers to a data value. Little x does. Little n is the number of data values that you have in a sample, and capital N denotes the number of values in a population, right? So we make this distinction between little n, sample, big N, population. And so there's a lot of distinction in statistics with the notation that we use for samples and the notation that we use for populations. This is the first that you're going to see, right? So sample size is little n, population size, capital N. All right. And here's another example. So X bar, right, is the one that you see at the top of the page, X with a line over it. We say that X bar, it's the mean of a sample. But mu, right, another Greek letter, right, you see that sort of in the middle of the page. Mu, it's kind of looks almost like an M with a tail on it. So mu is the mean of all of the values in a population. So if you're able to have all of the values in the population, PS, usually we aren't able to. We use the sample mean to sort of estimate the population mean in general. But if you were able to have all of the values in a population, then you could calculate mu, the population mean. But most of the time in here, we're going to be calculating X bar. So the way it's calculated is right in the middle of the top. Let me circle it here. maybe I can highlight it. I'm talking about this right here, right? So X bar is equal to sigma X. That means add up all of the X values. So the sigma, right, means sum or add, right? We're going to add up all of the X's that we have. We're going to divide by the number of X's that there are. So this is what I mean by the notation is different, right? So the notation for the way we calculate the mean is different from what you called an average, but the process that we do, right? The steps involved are exactly the same. And then similarly, the population mean is calculated by summing up all of the data values. In this case, you have all of them, and then dividing by capital N, which is your population size. All right, so let's look at this guy. Data set 32, airport data speeds in Appendix B includes measures of data speeds from smartphones from 4 different carriers. Find the mean of the first 5 data values. All right, so it's going to look like this. And these are apparently in megabits per second. I'm not exactly sure what that is. All right, so let's look at this, right? It's a sample because we're not looking at all data speeds. We're just looking at some. So we're going to say X bar. Oh my gosh, please, no. I don't know what I'm going to do if this continues all semester. Well, yeah, I need to figure out what's going on. And this is the second tablet that's doing the same thing. So I'm not sure what to try next. All right, so X bar is the sum of the X's divided by little n, the number that there are. Okay. All right, really? So this is going to be in the numerator, the sum of the X's, right? This is like X sub 1, X sub 2, oh my gosh, right? X sub 3, right? And we have in total 5 of them, right? So here N is 5. It's going to make me crazy. All right, so we're going to have 38.5 plus 55.6. We're going to add up all of our X's, right? Plus 22.4 plus 14.1 plus the last one, 23.1, right? We're going to add up all of those values. We're going to divide by 5. So let me get my calculator out. Maybe if you have one on you, you'll do the same. So 38.5 plus 55.6 plus 22.4 plus 14.1 plus lastly 23.1. I get 153.7. This is how I would like you to work these out. So 153.7, we'll divide that by 5, and we're going to round to 2 decimal places. So we're going to talk at the end of this section about round off rules, and the round off rules for the mean, or the round off rule for the mean, is that you go out 1 decimal place beyond what you already have. So the data goes out to 1 decimal place, right? You go out to 1 more with your mean. So the mean should go out to 2 decimal places. And then, oh, I guess I did know what that meant. Megabytes per second. All right. All right. So that's how you're going to write your answer, right? So you're going to use the round off rule, and then you're going to include your units, right? So that is the sample mean for this data with a sample size of 5. If it were a population for some reason, if those 5 values constituted some kind of population, the value would be the same. It would still be 30.74 megabits or megabytes, but you would call it mu instead. And your sample size would be capital N instead of little n. All right, caution. So you've heard me throw out average a lot because that's a word that you're familiar with, but in the world of statistics, we don't use it. So never use the term average when referring to a measure of center. The word average is often used for the mean, but it's sometimes used for other measures of center, right? So statisticians don't use average, right? It's not used in the statistics community or professional journals. So beyond this lesson where I talked about it because it was relevant, beyond this, what you've always thought of as the average, we're going to now call the mean in here, right? So we're going to sort of get rid of this word and replace it with the mean. All right, the median of a data set is the measure of center that's the middle value when the original data are arranged in order of increasing magnitude, right? It could also be decreasing. So your data values are in order from smallest to largest or from largest to smallest. It doesn't matter as long as you have them in some kind of order. All right, the median doesn't change by large amounts when we include just a few extreme values. So the median is resistant more so than the mean. The median does not directly use every data value. For example, if the largest value is changed to a much larger value, the median doesn't change. So what they're saying is if you have 1, 2, 3, the median is 2. But if you change this to 1, 2, let's do it over here. 1, 2, of course that happens. If we change it to 1, 2, 100, right? 100 is your outlier there. The median is still 2. So let's think about this. Let's just think about it for a minute. Come here, you. Come here, you. All right. So if you had 1 to 100, right, the median would still be 2. But here, here, a lot of times we call the median x tilde, right? So the median would be 2 in both cases. So down here, it would also be 2. But here, the mean would be, well, 2. So 1 plus 2 plus 3, right, is 6 divided by 3 is 2. You get 2 for your mean. But here, if we wanted to calculate the mean, well, we'd have 1 plus 2, 3 plus 100, 103 divided by 3, which is like 34 or something, 33 and change, whatever it is. It's going to be, I'll just say around 34, right? So the mean has been really, really, really affected by this 100, where versus the median didn't change at all. That's what we mean by that. So the median is resistant. The other thing we say sometimes is we say sensitive. So the median is resistant, meaning it doesn't, it's not affected by outliers. And the mean is sensitive to outliers, right? So if the mean is sensitive, it means it is affected by outliers. The median is resistant, meaning it's not affected by outliers, right? So the mean is sensitive versus the median is resistant. Okay, moving on. The median of a sample is sometimes denoted by x tilde. I already showed you that. It's x with sort of a funny squiggly line on top. We say it tilde, or like a boldface M, or just MED for median. So to find the median, we're going to sort the values. And then there's 2 different procedures. One, if the number of data values is odd. We already saw it. So let me just sort of show you what we're talking about here. If the number of data values is odd, like we saw in the last example, right? If I have 1, 2, 3, you're going to end up with one number in the middle, right? And you're just going to grab it. You're going to grab that number in the middle. But if we have an even number, let's say you had 1, 2, 3, 4, well, now you have 2 numbers in the middle. And what you'll end up doing is averaging these 2 values. So for this set down here, you would average 2 and 3, and you would say the median is 2.5, and the top set it was 2, right? So there's a different set of procedures that we work with when the number of data values is odd versus when it's even. Okay, so find the median of the first 5 data speeds for Verizon. So first thing is, right, well, we have an odd number, so there's going to be one number in the middle, but it would be wrong to say that this is the median because it comes in the middle. So it's only the median if the data set is ordered. So that guy's not the median. First, we're going to put them in order. So 14.1 comes first, 22.4, 23.1, 38.5, 55.6. All right, those are our 5 data values. Come here, you. All right. And so the number that comes in the middle is our median. So X tilde, right? The median is, in this case, 23.1. We really should go out to 2 decimal places, 10 Mbps, right? That is your, well, that is your median value. I was going to try to circle it, but I'm going to just maybe not try to do that. All right. So now we're going to repeat it. But they added a 6th, right? They added a 6th value. And so the first thing I'm going to do is I'm going to order them. And again, you could go greatest, you can go largest to greatest or greatest to largest. So just to show you that it doesn't matter, I'm going to start with the largest data value this time. So I'm going to say 55. 55.6. Oh gosh. 55 point, I feel like maybe it's an area, like maybe it's this area for some reason that does it. 55.6, and then I'm gonna go 38.5. So I've used these two just to help me. And then I'm gonna go 24.5. And then I'm gonna go 23.1. I'm gonna go 22.4, and then the last one, 14.1. So now I have them ordered from greatest to least, greatest to smallest, greatest to least, however you want to say it. And now I'm going to have 2 values that are in the middle. So I'm going to end up averaging the 2 in the middle, right? So these guys come in the middle, right? My middle is sort of here, right? If I'm in between these 2 values, there's 3 data values to the right. There's 3 data values to the left. So this sort of imaginary spot here is the middle. And so the median is going to be the average of those 2. So I'm going to say 24.5 plus 23.1 divided by 2. I'm going to average those. So it's 47.6 divided by 2, and then whatever that is. That's going to be my median in this case, right? And that happens when you have an even number of data values. So 47.6 divided by 2, 23.8, right? The median here is 23.80 megabytes per second. It's a real problem. Okay. So that is my lovely, that is my median. All right, just leave it. All right, mode is the data set that occurs with greatest frequency, right? A mode can be found with qualitative data. A data set can have no mode, it can have 1 mode, or it can have multiple modes. When 2 data values occur with the same greatest frequency, each one is a mode, and you have a data set that's bimodal, right? Bi meaning 2, right? So 2 modes, bimodal. When more than 2 data values occur with the same greatest frequency, each mode, or each is a mode, and the data set is said to be multimodal, right? So we have bimodal, we have multimodal, you could have unimodal, they don't talk about that, right? 1 mode would be unimodal. And then if there is no repeated data value, we say that there's no mode. So if we're talking about this set here or this set here, those are data sets that have no mode, right? There's no data value that occurs more than the other. They all occur just once. All right. So let's say that these were your data speeds. Apparently these are sprint speeds in megabytes per second. Notice that 0.3 occurs 3 times. And so that is your mode. So the mode is going to be 0.3 because it occurs most often, right? This is unimodal. So if you had a data set 0.3, 0.3, 0.6, 4, and 4, you'd have two modes because 4 occurs twice, 0.3 occurs twice. You're going to have two modes, bimodal. And then if they were all different, none of them occurred more frequently than the others, you'd say that you have no mode. Okay, so the mid-range of a data set is the measure of center that's midway between the maximum and the minimum values in the original data set. It's found by adding the maximum to the minimum and then dividing by 2. So you're averaging that minimum value and the maximum value. Because the mid-range uses only the maximum and minimum, it is sensitive to extreme values, so it's not resistant. It's sensitive, not resistant. In practice, the mid-range is rarely used, but it has 3 redeeming features. It's super easy to compute. It helps reinforce a very important point that there are several different ways to define a center of a data set, the center of a data set, and the value of mid-range is sometimes used incorrectly for the median. So confusion can be reduced by clearly defining the mid-range as something different than the median. All right, find the mid-range of the Verizon data sets. So let's just make that distinction. So X tilde, the median is what did we say it was? So 14, 22, 21. So it's 23.1, right? The middle value, if you order them, we did it already. So the median X tilde is 23.1. And the mid-range, well, it's the average of the high value, right? This is the high value, right? That's your maximum and your minimum. So, and I don't know that there's a special, I've never seen a special symbol that we use for this. So I'm just going to write it out. The mid-range is 55.6, lovely, plus 23.1. And then divided by 2. So this is, what is that? 78.7. 78.7 divided by 2. So you get 39.35 megabytes per second. 39.35 mega. Lovely. All right. And then the units, will it let me do it? All right, well, you get the idea, right? That is the answer here.
Supposed to let me walk on water?
All right, so round off rules for measures of center. We've already talked about it a little bit. For the mean, the median, and the mid-range, carry one more decimal place than is present in the original set of values. So if your data values are whole numbers, no decimal places, you go out to 1 with your mean, median, and mid-range. If your data values go out to 1, well, then your measures of center, the mean, the median, and the mid-range go out to 2. So you go 1 more then. And even when you don't think you would have to. So let's see if we can go back here. You saw me do it. Here, right? So this actually divided out to 23.8 exactly, right? When you put it into your calculator, 47.6 divided by 2 will give you 23.8, right? Even though it ended there, right? I'm going to add that 0 at the end, right? So because the data has 1 decimal place, my median, was this the median? Median should have 2. Mode it's not necessary. So when you have the mode, you don't round it, you just leave it as is. All right, so for the mode, leave the value as is without rounding because the values of the mode are the same as some of the original data values, right? So no need to round for the mode, but the mean, the median, and the mid-range, one more decimal place than the original data. All right, we can always calculate measures of center from a sample of numbers, but we should always think about whether it makes sense to do that. We should also think about the sampling method used to collect the data. All right, critical thinking and measures of center. See each of the following illustration or illustrating situations in which the mean and the median are not meaningful statistics. So A, zip codes of the Gateway Arch in St. Louis, the White House, the Air Force, Division of the Pentagon, the Empire State Building, and the Statue of Liberty. So these different historical locations, right? The Gateway Arch, the White House, the Pentagon, the Empire State, and the Statue of Liberty, right? They're zip codes. And so you see them there, 63102, 20500, 20330, et cetera. And we could calculate the mean, but what would that mean, right? There doesn't make sense to talk about the average, or there I go with that word that we shouldn't use. So the mean zip code, right? Because it doesn't measure anything. The numbers are just labels for geographical locations. So in that case, you could calculate it, but it doesn't make any sense, right? It wouldn't be meaningful. All right. So ranks of national universities. Harvard, Yale, Duke, Dartmouth, and Brown, right? They have orderings 2, 3, 7, 10, and 14. So you could take the average of that and get the average ranking. But again, no measures or counts here. So it doesn't make sense to talk about really the mean or the median. All right, so we're going to look at a couple of different ways to calculate mean. So this is going to be a mean from a frequency distribution. So you already have a frequency distribution and you want to calculate the mean. So first thing I want to say about this is going to be an approximation. And the reason it's an approximation is because you're using the class midpoints. You're not using the actual values, right? So I know I told you X represents the individual data, right? Each data value is an X. Here, in this formula here, X represents a midpoint. So it's the midpoint for each class. And so because you're not using actual data, but you're using the midpoint, this is going to end up being average. Sorry, this is going to be my son came in and distracted me. This is going to be an approximation for the actual mean, right? It won't give you the actual mean. So formula X bar, right? Notation is the same. So X bar is equal to the sum of F times X. So here, F is a frequency, X is a midpoint, and then you're dividing by the sum of the Fs, right? The sum of the frequencies, right? So you have the sum of the frequencies times the midpoints, right? For each class. And then you divide by the sum of the frequencies. All right, so this is the way it works. So remember, this is a frequency distribution that we created, not in this video, but several videos ago. I feel like it was like maybe 3 videos ago, right? Remember, we worked with this data. This was the drive-through data, right? And we created, this would actually, not even the bottom, but this here. Let me get rid of that. All right, so just this here would be the frequency distribution, right? Created from real data. So just this up to here, right? That's your frequency distribution. And we have, remember, 1, 2, 3, 4, 5 classes, right? We worked with this data a lot. For each class, we have the class midpoint, right? So the class midpoint for the first class, right? It's the value that comes in the middle. If we average 75 and 124, we would get 99.5. That's the class midpoint. We're going to have 5 of them. And so for each class midpoint, we're going to multiply by the frequency, right? So this number here, this 1094.5, that came from 11 times, right? 11 times 99.5. If you put that into your calculator, 11 times 99.5, you're gonna get that value there, right? That's where that came from. And so that's F times X for the first class. And you're gonna keep doing that. You're gonna do that for each class. So you're gonna end up with 5 of these values here. So this guy here, for instance, right? He's F times X, the frequency, right? Which is 3 times the midpoint. So this value is 3 times 249.5. If you put that into your calculator, you should get 748.5. So you're going to do that 5 times for each class. You're going to calculate the frequency times the midpoint. You're going to get a quantity here, and then you're going to add those up, right? So when we take the sum of F times X, right, it's the sum of each frequency times the midpoint, right? And you keep doing it until you are done with all of your classes, right? So I'm going to do that 5 times, right? So I'm going to calculate F times X for the first class, F times X for the second class, F times X for the third class. And then at the end, I'm going to add these guys all together. I'm going to take the sum of F times X, right? That's 8,025, right? That came from 1,094.5 plus 3,588 plus 1,995 plus 748.5 plus 599. If you add them all together, if you take the sum of F times X, you're going to get 8,025. The other piece of information that you need here is the sum of the frequencies. By the way, that's just going to be your sample size. It's just going to be your sample size, right? But if you add up all of your frequencies, 11 plus 24 plus 10 plus 3 plus 2, right? If you add up your frequencies, you're going to get the sum of F, right? The sum of F. And why do we need that? Well, it's part of our formula, right? So I have the sum of all of my frequencies. Remember, that's just the same as N, right? That's your sample size here. And then I have the sum of F plus, or F times X. And so notice that is what I need in order to calculate X bar here, right? And it's an estimation. So X bar, let's see if I can do it over here. So X bar is going to be the sum of F times X. And we're dividing by the sum of just F. All right, and the sum of F times X is, what is it? 8,025. And the sum of the frequencies is just 50, right? That's our sample size. And so this will go into your calculator. And you'll get an estimate for the sample mean, an estimate for the sample mean. All right, so that goes right into your calculator. All right, so this is 160, 160.5. I'm going to go out to 2 decimal places. Actually, no, I only need 1 now that I think about it. Our original data, I believe, was whole number data. So I'm going to just call that 160.5, be done with the whole thing. And that is our estimate for the sample mean, right? And it's, I guess we should include units though. Remember, this is the drive-through times. So we're going to write seconds. This is 160.5 seconds, right? Is an average for, I'm sorry, is an estimate for the mean wait time at the drive-thru at McDonald's. All right, the last thing that we're going to look at is a weighted mean. All right, so the last thing we're going to talk about is calculating a weighted mean. When different X data values are assigned different weights, we can compute a weighted mean. So formula is going to be X bar, right? That's your sample mean. And there's that sigma, capital sigma again, it means add up, right? So the sum of W times X. So in the last example that we did, we had the sum of F times X. F was a frequency, X was your midpoint. Here, W is a weight and X is your data value. Okay. And in the denominator, we have the sum of the weights. And a really good application for this is calculating your GPA. In her first semester of college, a student of the author took 5 courses. Her final grades, along with the number of credits for each course, were she got an A in a 3-credit class, an A in a 4-credit class. So ours is 4, right? The A in this class, right, is weighted a little bit heavier than an A in your other classes, which might be 3. She got a B in a 3-credit class, a C in a 3-credit class, and she failed her 1-credit class. The grading system assigns quality points to letter grades. So A is worth 4 points, B is worth 3 points, C is 2, D is 1, F is 0. So this is sort of standard. And we're asked to compute her grade point average. So I think I can do it here. I think I can do it right here. So it's going to be X bar is the sum of W times X, right? The weight times the data value, and then divided by the sum of the weights. That doesn't look good, does it? I'm not exactly sure even where to go to get help on that. I've been using these tablets since COVID, since we started teaching online. And if it was just one of them, then I would say, well, I need a new tablet, but they're both doing the same exact thing. So I'm just not sure. Okay. And you could make a table. In fact, you know what? Let's make a table here. So I'm going to write the weights, right, which are going to be the number of units. And I'm going to write, oh my God. Gosh. Is it like a speed thing? Maybe it's a speed thing. No, I don't know what it is. Apologies, I'm sure this is just as annoying for you as it is for me. All right, let me try one more time. Okay, well, there we go. All right, so the weights are going to be the number of units. So for this first A, let me write it over here. It's not really part of the problem, right? But we got an A in a 3-unit class. We got an A in a 4-unit class. We got a B in a 3-unit class. We got a C in a 3-unit class. And we got a, oh no, we got 2 A's. 2 A's, a B, C, and an F. 2 A's, a B, 2 A's, a B, C, and an F. Yeah. And an F in a 1-unit. Okay, so these are my weights, right? Everything here, the 3, the 4, the 3, not the letter grades, but the numbers here are the weights. And the data values, well, those are going to be the points assigned for each grade, right? So my A is going to give me 4 points. My A here also 4 points, right? The B is going to give me 3, the C is going to give me 2, and I get 0 for my F. So now I want to calculate a couple things. I need the sum of the W's, and I need a sum of W times X. So I need a third column here. This is going to be W times X. So each grade times the weight. So this is going to be 3 times 4 or 12. And then I'm going to have 4 times 4, 16. I'm going to have 3 times 3, 9. 3 times 2 is 6. And then 0 times 1 is 0. All right. So now I have everything I need to calculate the sum of W times X and then the sum of the W's. So the sum of W times X is the sum of this column. So 12 plus 16, 28, plus 9, 37, plus 6, 43. All right, so that goes in the numerator here. And then I'm going to add up the W's. So the weights, so 3 plus 4 is 7. Plus 3 more is 10. And then plus 3 plus 1, we get 14. All right, so my sample mean here is going to be 43 divided by 14. Rounded to 2 decimal places, right? We get 3.07, right? That's her GPA for the semester. Oh, yeah. All right, GPA is 3.07 for the semester. And you could do this for, right, your whole college career. You could put all of your classes on here. But this is just for, right, the grades that she got this one semester, 3.07. And round off rule here, remember, right? So our data values are the number of points you get for each grade. And they're whole numbers. And so normally the round off rule, by the way, would be 1 decimal place. The exception to the round off rule is something like this, where GPA are always rounded to 2 decimal places, right? You never see a 3.1 GPA or 3.074. They're always 2 decimal places. Money would be another exception, right? So if you had whole number amounts, right, 10 and 15 and 25, and you found the mean of those, right, you wouldn't round to 1 decimal place, because we never would say, you know, $10 and $10.1, right? We never say that. We say $10.10. And so money would be another exception. GPA, money, these are things that are exceptions to the round off rules. All right, so they're telling you, maybe they have a nicer version of, well, no, they just have the same answer as me. All right, that's all I have. I am going to try and figure out what is wrong with my tablets between now and the next time I have to record a video. I hope that you have a great week, and I will see you in week 3, right, to finish up the chapter 3 material.